Hello, welcome everybody to this new installment of this second series of the MICGen, where we like to bring together experienced researchers from our community together with younger researchers or at an earlier stage in their career to have an afternoon European time where we can interact around the use and of modeling and its exploitation in different areas. Today's event will be around the use of simulation and modeling for colloidal systems, and we will have a set of nice speakers. Our experienced speaker today will be Emanuela Zaccarelli from La Sapienza, and we will today have three younger speakers. One will be Assad Sulk from Ben Gurion, and Fergus Moore from Bristol, and Luca Tonti from Manchester. And before we, and there is always then a second part of this session where we will move to this to the gather room to have the possibility to carry out more informal meetings, to have the possibility to discuss among all participants more and less experience, and where there are also today 6 posters presented, and then the poster presenters will be around also to interact with all of you. Before we start this first part of the session, go move to the science. I had a couple of slides with technical information. First of all, being online, and I remind you that this event is recorded. Actually, all these MICGen sessions are stored in our CCAM YouTube channel and also on our CCAM website. So you can go and see what has happened before, what have been the different topics and speakers. Then regarding how this first part, all the interaction that you may have with us is through the Q&A functionality in Zoom. For the first talk, the one by Emanuela, that will be more extended, you can ask questions, you can type your question during her presentation, and then I will be relaying the question to her along. So that provides also a possibility of having more an interaction, or she can receive feedback about how are the questions or issues that raised from her presentation. And then at the end of her presentation, then we will have a more extended Q&A session, where then you can pose the question verbally. So in that second part, there is no need for you to type your question. It's simply enough that you indicate that you want to ask a question with a word or with a symbol, with a hand, and then we will unmute you, and then you will be able to ask the question. And this also makes it possible to have a dialogue depending on how the replies go. You can build on it, and it's more an interactive moment with the speakers. In the case of the other 3 presentations that are shorter, I will not take questions during the presentation. We will have then the same Q&A at the end of each of these 3 presentations. And the procedure will be the same. You simply indicate your interest to ask the question, and then we will unmute you. I will tell you then when you can pose the question, and then we will sustain the same type of conversation with all presenters. You will not be able to activate your video during the duration of the Zoom. And as I said, the chat is not available, so that all communication is channeled through this Q&A. I take now, before we start, the opportunity to remind you of forthcoming online activities. Actually, in the month of January, we have a series, a CCAM Marvel Classics in Molecular Materials Modeling, where we invite those who have developed and invented new algorithms that have become a classic, a reference for the community, to present these algorithms, how they emerge, what has been the impact that they have had. And then there is a second part that is more informal about what was the process of creation and what does modeling and research in that area means to them. So then the next installment, again, this is a series, and they are also recorded, and the past ones are available on our YouTube channel or on our website. The next one will take place on January 18th, 4 p.m. European time, and it will be about ab initio studies of electronic excitations using many-body perturbation theory. The speakers in this case will be Lucia Reining from the École Polytechnique, Steven Louis from University of California, Berkeley, and Rex Godby from the University of York. And also at the end, these mixed gen installments take place every month. There is one every month. So the next one will be at the end of January. This will be a session on simulating quantum materials, and the experienced speaker will be Antoine Georges for École Polytechnique. And during the month of January, then we will also identify the younger speakers. And again, I invite you to check what is the final content and to participate also in this new mixed gen event. As I said, previous sessions are available, so you can look at them, and also you can also register to our webinars mailing list using, or you can also follow us on Twitter, and that's also will give you if you do that, then you will be receiving these advert announcements in due time. And I wanted to finish also by advertising a slightly different type of event that will take place in February. February 11 is the UN Day for Women and Girls in Science, and we have thought in organizing an event about women and girls in computer, in modeling and simulation. And we will do that by having a conversation with 4 scientists in different stages of their careers, so that then can provide a broad view of what has been doing research in modeling and simulation as a woman. And so it will be a pleasure to have Ruth Lindenbell from Cambridge, Julia Galli from the University of Chicago, Clemence Corminbeuf from EPFL, and Magali Benoit from CNRS Toulouse. Again, it will be called From Women's Eyes. You will receive, and we will announce it in due time, and you are also invited to attend. So with this, I finish this short introduction and small advertising, and now we move on to the science of this part of today's event. So it's a pleasure to give now the floor to Emanuela Zaccarelli from University of La Sapienza in Rome for the first presentation. So please, Emanuela.
So thank you very much. Thank you for the opportunity to present some work. Let me just share my screen. You see it?
Yes, we see it.
Okay. So when deciding what to talk about, I was a little bit in doubt, and so after some thought, I decided to talk about anomalous low dynamics in soft matter, which will give me a little bit of opportunity to present some simulation that we performed in the last years. And I do want to apologize because I will talk about not very recent stuff. So there are many experts I see in the audience. I hope you will not be too much disappointed by knowing already most of the things. But at least I can tell you a story that started about 20 years ago or even more, and let's see what is up there today. So the outline of the talk is that I will start with some introduction, in which I will basically define what I mean with this anomalous low dynamics. And to do that, I will give the examples of the standard glassy behavior. And I will introduce a bit the theoretical framework that allows us to understand, also in computer simulation, this anomalous low dynamics. And then I will report all data about the first example of this behavior, peculiar behavior that was found in soft matter that are colloids plus short-chain non-adsorbing polymers. That means colloids with depletion interactions. Then after this first introductory part, I will talk about some other examples of anomalous law dynamics that were seen later. And I will focus on a particular case that is called the modified Lorentz gas, the way we call it. And finally, I will give some conclusion and perspectives. So since I am talking about glasses and about soft matter, I have to start with the simplest model, the one I love very much, and I'm very, very fond of this picture that Peter Pusey once gave me, and I put it on my wall in my office. So this is the famous experiment by Peter Pusey and Bill Van Meegen, which appeared in Nature in 1986, where they studied colloidal hard spheres phase diagram. So they prepared a set of samples at different packing fractions, and they studied the fluid to crystal transitions. And then what we will focus more today is about the onset of the glass transition around packing fraction 58%. Bill Van Meegen then continued for a long time to work on hard spheres. Here is a picture from his very famous paper of with Sylvia Underwood in 1993, where he basically measured the correlation, the autocorrelation function of the density that is defined here, normalized by the zero time value. By dynamic light scattering. So for these glassy samples that I put here, these are the density correlation function as a function of packing fraction at a fixed wave vector that is typically of the size of the diameter of a particle. And what happens from these measurements? For now, let's concentrate on the symbols, which are the experimental measurements. We will go back to the lines later. At low packing fraction, you see that there is a single relaxation. And then as you increase further and further the packing fraction and you approach the glass transition, what happens is that there is a second decay. And then if you further increase the packing fraction above 58%, the system becomes arrested, and on the time scale of these measurements, the system arrests. Of course, later there have been other measurements, for example, by Luca Cipelletti's group, that have extended largely this time window, but for the purpose of this talk, it is sufficient to focus on the old data of Bill Van Meegen. One important point that I want to underline is that, as you saw before in the previous slide, here we have the fluid crystal transition. But in the experiments here, we see no sign of crystallization because colloidal hard spheres are intrinsically polydispersed. And so polydispersity suppresses the tendency of crystallization. So this two-step decay, so-called, is the typical feature that happens close to a glass transition. And in the hard sphere in particular, it is very easily understandable in physical terms by means of the so-called cage effect, in which basically when you start to pack the hard sphere more and more, a given particle will feel more and more the influence of the nearest neighbor. And so there will be a short time relaxation when this red particle is able to explore basically its cage, so the cage of the configuration in which you started the measurements. But then to diffuse away from the initial configuration, you need to have some kind of rearrangement of the other particle that allows to go out from the initial configuration. And the time that the red particle takes to explore this cage becomes longer and longer. You see that here you have a logarithmic time scale, and this is usually what you have to use for when you study the glass transition. This time extends by decades until the system arrests on the time scale of the experiment. Now, if we do computer simulations, for example, nowadays you can do it also with experiments, but in computer simulation, sometimes it is much easier to look at the mean-square displacement of a given particle as a function of time. And I report here the results of molecular dynamics simulation of our spheres that we performed some years ago, just as a representative to show you that basically the same feature that happens in the density correlator, that there is this plateau emerging, also happens in the mean-square displacement. Here I report results for R-sphere simulation of packing fraction from 54 to 59. And what happens is that basically there is this plateau originated from the gauge effect that becomes longer and longer. One thing that I want to stress that will be important in the following is that the plateau height of this plateau for the half-sphere glass transition is basically always the same and is roughly of 0.1 of sigma, where sigma is the size of the particle, so a 10%. So the particle can usually, before becoming glass, you can explore 10% of its diameter in the cage. The other point that I want to make is the importance of polydispersity. So as I said above, in the experiments, in colloid experiments, so usually, I mean, there is the tendency to not observe crystallization because of polydispersity, because it is very difficult to have samples that are really monodispersed. In simulation is the opposite. So if you just simulate monodispersed R-spheres at around 54, 55, they will immediately crystallize. In the simulation that we performed in collaboration with Chantal Valeriani and co-workers and the group of Edinburgh and Peter Pusey as well, we explored the different polydispersity for these R-spheres in the low polydisperse limit that is typically 5%, 6%, that is the one that is achieved in experiments. And you see actually that each of these curves is for many different polydispersity, the ones where the system did not crystallize, and basically tells you that there is not a crucial dependence on polydispersity. So the MSD that you measure are basically invariant. The important point is that otherwise, I mean, you really have to include polydispersity, otherwise your system will crystallize and you will not be able to explore so many decades of relaxation. Now, I decided to talk about this because it gives me also an opportunity to give my personal tribute to Professor Wolfgang Goetze, that was one of the greatest maestro that we had in soft matter, that unfortunately passed away about a month ago. And most of you know him, but perhaps the young generation does not. And since I had the privilege to know him during my PhD and also to work with him a bit because he spent a sabbatical in Rome, I am very honored that I have the possibility to give this talk that basically intertwines simulations with the mode coupling theory. So in fact, the lines that I anticipated in the Van Meegen figure are predictions of the mode coupling theory that was invented by Goetze and co-workers. And actually Wolfgang, when he was in Rome, when I met him, was frantically working at his book that he left us today, so that if you are interested, there is this treasure that you can study to know a bit more about mode coupling theory. And I talk about this because basically this is the tool by which we will understand this anomalous law dynamics. And so mode coupling theory is actually a theory for the equation of motion of the density correlators and equivalency of the mean-square displacement that, as I showed you up to now, are the observables that you have to look if you want to monitor the glass transition. So you have this arrest transition that happens. And through the mode coupling theory, you can write an equation of motion for the density correlator, phi of Q. And this equation of motion contains an integral term. It's an integral differential equation. And the crucial approximation of the theory is the choice of this memory kernel. The mode coupling theory writes this memory kernel as a functional of the density autocorrelation function, so that you have it here and you can solve these equations. And this functional is an integral which couples different modes by which the theory takes its name, mode coupling, by means of static coefficient. So the important thing is that it's a theory in which, when you know the static coefficients that are called, that are these view coefficients that only depends on the static structure factor and on the number density of the system, you can basically calculate the full decay of the density correlator. This is what Van Meegen did in his paper. And then the important thing is that the Mock coupling theory qualitatively reproduce the feature, because you can see that the theory really reproduces well the data, except for the fact that the theory would predict the onset of the transition at a much smaller packing fraction, that is 0.52. But to our purpose today, this is quite irrelevant, because the important thing, and how Van Meegen plotted the data, and how we will do it also later, is that you need a mapping. You need to know where your experimental or numerical glass transition is. You basically shift the Mock coupling theory predictions to the expected critical volume fraction, in this case, or temperature for glass formers, and then you can basically reproduce the behavior of the density correlators around this transition. An important thing is that Mock coupling theory is able to calculate analytically the behavior of the density correlators close to the critical point, so close to the transition. And basically the correlators can be expanded in a series of a given time function. So it factorizes the dependence on Q with the dependence of time. And Professor Goetze and co-workers has showed that basically approaching and leaving the plateau of the transition, this G of T, this is called the beta correlator because it describes the beta relaxation, has a power law form. It is T to the minus A going to the plateau and T to the B leaving the plateau. And these A and B are coefficients that are related to each other by this mathematical equation, and they are defined once and for all. So they only depend on the interaction parameters, on the structure factor, and on the number density that you input. So why am I saying that? Because basically I just want to say that for a standard glassy behavior, you have this two-step decay, and this the plateau behavior is described by power laws. The same applies to the mean square displacement. Goetze and co-workers, also Matthias Perl later, this is actually taken from a paper from Matthias Perl, they did the same expansion, critical expansion for the mean square displacement, which follows a similar behavior, also power law, and this fits very well the data of our spheres. So you have experiments and theory again. So I just want to finish this introductory part saying that this two-step decay is a generic phenomenology of the glass transition. And this is the famous article by Walter Kobbe and Anderson about a binary mixture Lennard-Jones, a binary mixture because otherwise if you take just the monodisperse, the one component Lennard-Jones, it will crystallize. You see that the behavior in temperature, now that is the relevant control parameter, a fixed packing fraction, is you have this onset of two-step decay in the density relaxation, self and collective. Here is the self. And the mean square displacement also shows this typical behavior that I showed you before. And I put it here just for completeness. This power law dependence of the critical dynamics in the density correlators also manifests as a power law dependence of the transport coefficients, like long time self-diffusion coefficient or relaxation time close to the transition. Then there will be deviations at even lower temperature, but to describe the approach to the transition, the Mock coupling theory is quite accurate. You see that you have here in the Lennard-Jones mixture several orders of magnitude where the behavior can describe the data, the numerical simulation. Okay, so this is just to say that in standard glass transition, you have slow dynamics that happens via a two-step process. Instead, what I call anomalous glassy dynamics is sorry, I see a question, but should I answer? Should I read it? Ignacio?
Sorry, yeah. I was going to tell you I was muted. Yes. So there is this question by Vishnu Krishnan. How do we know that there might be a thermodynamic transition in experiments or simulations? What if the second decay from the plateau is just postponed to later and later times with increasing packing fraction, therefore never becoming purely caged?
Okay, so this is a nice question. So let me go back. Let me close. I have the window of the question in front of my computer. So for example, here, okay, so what I'm telling you with the simulation I'm showing and also the experiment, except for the two data sets that were really arrested, they are in equilibrium. So also this simulation by Walter Cobb, but also the ones on our sphere I show you, they are equilibrated systems. And so you can, for example, change the time at which you start measuring your mean-square displacement of density correlation function, and they will be always the same. So if you find what you mentioned in the question, that the plateau is just postponed, it means that you are out of equilibrium, and this is a well-known feature of glassy systems, that is aging. And so you have to be sure when you do, at least when you do your simulations, that you are in equilibrium. Otherwise, you must monitor the dependence on the starting time of measurements and monitor the aging dynamics. So what I showed you so far is all equilibrium. Okay.
Okay. Yeah. Yeah.
Okay. So I go ahead. Yeah.
Yes.
Okay, so now anomalous dynamics. I cannot remove this thing anymore. Okay. I have something, the question appeared and I cannot remove it from my screen. And it covers my slides, sorry. Okay, so what I want to talk today is when instead of the two-step decay, there is a different behavior for the glassy dynamics that I call anomalous. And this was first observed in mode coupling theory, and in particular in schematic models of the theory that I will go back in a minute. And basically, in this kind of situation, instead of having a standard two-step relaxation for the density autocorrelation function, you see that you don't have the onset of a plateau, but what you have a logarithmic decay which becomes longer and longer in time. And if you solve the critical dynamics of the density correlators close to the correlation, instead of having the sum of power laws, you will have the sum of logarithms. As shown here. And at the same time, if you monitor the mean-square displacement, you saw that there is a similar kind of behavior. You will have the onset of power law description with power laws, but with a subdiffusive behavior. And so the logarithm of the intermediate scattering function becomes, instead of having a flat plateau, you start to develop these subdiffusive regimes. Okay. And the way that this anomalous dynamics occurs is by the fact that in the theory there arise higher order singularities. That is, that the system could have in the phase diagram different glassy states, and these different glassy states at some point they merge, they coalesce in a higher order point. So to be more specific on this, I want to show you a little bit of this with the simplest model, which has a higher order singularity that in the decoupling language is called the F13 model, in which the functional of the memory kernel, which depends on the vertex, thermodynamic vertex, and the density correlators, is just this simple object. If you solve the dynamics of this, you will see that in your phase diagram that is controlled by this V1 and V3, you have two glassy lines. You go from liquid to glass increasing V1 at fixed V3, but you also go from liquid to glass at fixed V1 increasing V3. And so what happens is that at some point you have that this glass here and this glass here will become identical, will merge, and you will encounter a higher order singularity that by the shape of this phase diagram was called A3. It was called a cusp singularity, and in mathematical terms of catastrophe theory is called A3. And you can mathematically define and calculate this higher order singularity because it is related to the second derivative of the functional. And when lambda, the critical exponent parameter, which define also the other exponent a and b I told you before, is equal to 1, you have the equivalence of the two classes. Interestingly, here in this little bit, in this part of the line, you can go from one class to the other, and it's discontinuous, the transition. While instead here, the two classes merge in a sort of, and then above this, the transition between the two classes becomes continuous in a sort of kind of, let's say, critical point scenario, but this is dynamic, and of course it's out of equilibrium and so on. So, of course, coming back to the question that I have been asked before, here you are in equilibrium. As soon as you enter in the glass, you are out of equilibrium. And so if you want to explore, for example, this glass-glass transition, this higher order singularity, you will have to pass through out of equilibrium state, and it becomes could become a bit difficult because of aging and so on. So actually, there is an even higher order singularity that it is actually more interesting. And to find it, you need to have a slightly more complex model in which now you have two modes. Before we had only one, like, so we have M1 and M2, the two functionals that are defined in this way. And basically here you have three now control parameters, V1, V2, and V3. So if I plot the phase diagram at fixed V3, for this particular case of V3, I find something that is basically identical to the one I showed you before. You see that there is a kind of similarity. But then now you have the possibility also to change V3. And changing V3, what happens is that this glass line shrinks. So this line moves up, and you see that this line merges with this other at another critical point that is called A4. And it's called swallowtail singularity because of the shape. And then above, if you further increase V3, then you lose this, and you will have just a single glass. But interestingly now, coming back to the question of equilibrium, now here you are in the liquid for this value of V3 until you arrive at the A4 singularity. And so, for example, you can do computer simulations going asymptotically close to this point and see if you find this anomalous dynamics, logarithmic dependence, for example, of the density autocorrelation function. But before going that, I mean, these were very nice results, but I think that Professor Goetze had most of them for a long time, but then the activity of working on this actually really flourished after 2002, when there was actually the confirmation of a similar scenario in a very, very simple system that is nowadays widely used in soft matter, that is short-range attractive colloid, which means half spheres plus non-absorbing polymers that undergo, so their sphere undergo a short-range depletion attraction. In 2002, there were two papers on that happened at the same time, these two papers. And in particular, I report the results of the group of Edinburgh of this famous science paper, in which also Matthias Fuchs, that was a collaborator of Professor Goetze, went to Edinburgh and simulated this activity. And now you see that the control parameters are the vacuum fraction, as in our spheres, and now you have the increasing concentration of polymers, Cp, that plays the role of a temperature. That would be one of these V2 and V3 things of the schematic models. But you see that basically what happens is the following. If you are at 0 polymer concentration, so here along this line, you have just hard spheres and you go from fluid to glass. We neglect, as usual, crystallization because the system are fully dispersed, and around 58% you have the occurrence of a glass transition, and the glass transition has this kind of shape as measured by experiment that goes actually towards larger packing fraction. And then up here, there is another glass line from fluid to glassy behavior. And the very interesting thing is that here, there are these green triangles that are systems that actually were able to crystallize. Okay, so basically, it's very interesting because here you go from something that is glassy, you at very large packing fraction, we talked about the cage effect, the hard sphere are very, very dense, you add the polymer, so you make it even more dense, but for some reason they speed up, you will see now in a minute, and they basically are able to go to underlying equilibrium, partially crystallize, but then you further add polymers and they glassify again. So doing the dynamic scattering experiments from the point A to H along this red arrow, this famous paper showed that the dynamics is actually reentrant. And so you start from hard sphere samples, the A point that is well arrested, similarly to the curve of Van Menge that you saw in the first slide. You start to increase polymer concentration, this goes down, then you increase it a bit more, it goes completely down, so you lose completely ergodicity, you lose also the two-step. You continue to increase the polymer concentration and you now have a second arrest, a different arrest. You see that the shape of this correlator is completely different from this, so it's a completely different glass. And actually, if I was able to enlarge this figure, here you would have a kind of a plateau, because what happens is that here the particles are much more localized, and so the two-step takes place at a much higher plateau value of the density correlator. And so this behavior was explained in terms of two different glasses. One that is driven by the topological cage, the one we talked about before, and one that is stabilized by the bonds, by the attraction. You put a lot of polymer, the particles stick more and more together, and let's say more similar to a dense, very, very dense gel. And interestingly, there was this reentrant behavior and the occurrence of these two different glasses. But the one I want to focus today is that if you then do the experiment here, more or less, and you try to go across this glass-glass transition, the dependence of the density correlator would be logarithmic, as the schematic models of MCT would have predicted. So this fantastic result triggered a lot of activity in this and a lot of computer simulations that were done at the time. And I just briefly present some results of our group in Rome, but let me remind you that there were a lot of other people that did them. First of all, Antonio Huertas, that was working in Edinburgh at the time. So in Rome, we concentrated as a short-range attractive colloid on a square well model, in which you have a hard sphere plus a square well of an attractive width delta. And what we did in Rome, since I told you from the initial slide of Van Megen that MCT will predict the arrest transition in the wrong place of the phase diagram. So what we did both mode coupling theory calculation and the numerical simulation of the exactly same model that was a binary mixture of square wells, because otherwise it would crystallize. And then we mapped onto each other simulations by extrapolating, for example, the relaxation time with the power law behavior, the simulation data that are these data points onto the prediction of MCT. The prediction of MCT were put forward for the square wall model in this work. And since this model is conceptually identical to the ones I showed you before, the schematic models, there is an A3 singularity here that happens in the glass, and where the system goes from the attractive glass to the repulsive glass. Okay, and now we wanted to do simulation and to verify the existence of the higher order singularity. But as I told you before, there was actually the question made me clarify. You are forced to be out of equilibrium, and this could have dependence of the initial waiting time. And so we then decided to do to learn from the theory and to slightly increase the range of the square well. And we worked at the particular delta for which basically this line, this glass-glass transition line, would shrink and merge the two glasses, and so this A4 singularity. And then we performed simulation at a given state point in the vicinity of the A4 singularity, so always in equilibrium, and we monitored the behavior of the density correlators. So doing that, for the A3, which means that we are somewhere here in the phase diagram, at delta that is 3% of the diameter, that is a very, very narrow width that is possible in experiments, because in experiment, you remember, you have these polymers that are much, much smaller than the colloids. And so if you calculate the density correlator of this simulation at different Q versus time, you find that you have this behavior. And since this is the predicted asymptotic behavior from the theory, you have a logarithmic term plus a logarithmic term squared and so on. But the coefficient of this squared logarithm depends on Q. And so there will be a characteristic Q vector, Q star, at which the logarithmic relaxation is enhanced. So if you're looking for the higher order singularity, typical anomalous dynamics, when you look in the density correlator, there will be a selected Q that will be a characteristic length that is important in your arrest mechanism, at which the logarithmic behavior is enhanced. So this was for the A3 point. We are very far from it. So if we then are able to calculate the A4 singularity correctly, and this we can do in simulation and theory, where we study exactly the same model. It's not the same in experiment, unfortunately. We can go much, much closer to the A4 than to the 3. And in fact, when we did the simulation for the expected well width that is 4% instead of 3%, you see that now we have a logarithmic window that basically is much, much more enlarged. We have 4 decades of logarithmic decay at a given Q vector. And you can imagine that these were very, very long simulation that we did a very long time ago. So but for that time, I think we waited several months to obtain these results. But these results really verified the fact that there was the existence of this higher order singularity and the onset of the anomalous dynamics. And similarly, we monitored also the mean-square displacement. And for the 3% case here, you have that basically you have subdiffusive behavior of this window. For the one that corresponds to the higher order singularity, this extends as it should, and you find the subdiffusive behavior for many, many decades as well. So this, I think, was a very, very strong confirmation coming from simulations that the predicted scenario of the Mock-coupling theory was working, and it opened up really a lot of activity on this. Let me try to give a hand-waving physical explanation for the anomalous dynamics. And if you're interested, you can read this commentary article that Francesco Ciortino wrote back then around this famous experimental results of Pam and co-workers. And so basically, let's try to give a physical explanation why this happens in this particular system. I told you in the beginning that for the repulsive glass, for the hard sphere, you have a localization length of the mean-square displacement in the glass, so that is roughly 10% sigma. And so you have this topological cage, and you are at a thermal energy that is much greater than the attraction energy. If you go in the opposite limit, you are stabilizing bond cage. You are at very low temperature with respect to the energy, and you are in this attractive glass. And in this attractive glass, particles are close to each other, and they are basically stabilized by the bonds. So if your delta, if your range of the attraction is very small, it will be sensibly smaller than the one in the repulsive glass. And so you have actually the competition of the two states. So this is the important ingredient, and it is why it happens only in short range attractive colloids, that you have to have a clear separation between these two landscapes. And then, so you can start from a repulsive glass at high temperature. You then start to lower the temperature. And when you go towards the thermal energy similar to the energy of the attractive potential, what happens is that some of the particles will statistically be closer and feel the attraction, some others not. And the fact that some of them, but not all of them, because these two energies are comparable, are probed, overall frees up a lot of available volume in the system, and that explains why the dynamics is re-entered, because this fluid is much faster than this. And then if you continue to further lower the temperature, then everything will be stuck, and that's it. And so in between, I can say in a little bit of hand-waving terms that basically the system is kind of hesitating between the two plateaus. Sometimes it feels one, sometimes it feels the other. And the result of it in this phenomenological explanation that, of course, Professor Gozzi would have never told you, is that you have this intermediate behavior that turns out to be subdiffusive. So this is just to give you a physical explanation. Okay, now after this very old work, let's go a little bit after in time. And at some point we asked ourselves, okay, but maybe this is something related to attraction. Maybe if for purely repulsive potential, you cannot have such a higher order singularity. And some years later, we moved from the square well to the square shoulder. And that is actually a model that, although very simple, is the simplest two-length scale model that is widely used in the community, because it can describe water, metallic glasses, other systems, and so on, and even some quantum ones. So it was interesting to study the dynamics of this. We started with the MCT calculation, kindly helped by Matthias Perlen in collaboration with Professor Stanley Group. And for a long time, we didn't find any higher order singularity, simply because we realized just only much later that actually, if you go from the liquid to the glass, there is no higher order singularity in the typical width of the shoulder that we were probing, but actually the glass line is now not directly going from the liquid, but is buried in the glass. And you have a glass line from here, from glass to glass, that has two endpoints. And actually there are two predicted A3 singularity in the square shoulder. And then, as we did in the square well, we can always play with another parameter, that is the width. And as you change the width, then these lines move closer to the liquid glass ones. And this, then you have two distinct glass lines with two distinct A3 points. And then if you continue, as we saw before, then one of these merges first, you have an A4 here. And then you continue to increase the width, you have another here, and you have another A4. And so what we did in Rome was to test this by computer simulation, because as I told you, we like to do this very, very long simulation in Rome. And so we simulated a binary mixture of square shoulder this time with different deltas. And then I will be brief. I just show you, sorry. I just show you, we chose this path here, approaching the A4 singularity predicted by the theory. And here you see that for this path, that at this particular delta and temperature and varying packing fraction here, you see that there is the onset of this very long extended subdiffusive behavior in the mean-square displacement, and the onset of the logarithm behavior, the logarithmic dependence of the density correlation function at this particular Q. Similarly, also the second A4 was confirmed. And in this case, these are the data for another delta and another packing fraction varying now temperatures. And we saw the emergence again of this subdiffusive behavior in the MISCO displacement and the logarithm here. These were very long simulations, and actually you may notice that these curves are kind of weird, because you first see the standard two-step relaxation also here, and then the logarithm comes much later, which is kind of intriguing. And this is due to the fact that we come here, and you see that when we come here, there is this liquid glass transition that the system feels before going to the fourth singularity, because the line is not like that. There is this shoulder. And the fact that there is this shoulder in a way kind of masks at the beginning. So if you simulate up to this temperature that was not close enough to the A4, you see that you would not notice that there is a logarithmic dynamics. But if you go then asymptotically close and are able to bypass the effect of the liquid glass transition, you start to see this behavior. So actually, all of these results gave us great confidence that there are these higher order singularities in MCT that really have a counterpart in simulation and experiments, and stimulated a lot of work in the last decade. So actually, just to be brief, I mentioned a few works. A lot of works have been devoted to binary mixtures. Asymmetric soft spheres were studied by Angel Moreno and Colmenero. Asymmetric star polymers, we studied them in collaboration with Christos Ligos, for example. And then there were also simulation of hard spheres in a porous matrix that were studied in the group of Gerhard Kahl. And not always there was a study like we did before for the square shoulder or for the square well, in which you had both theory and simulation. And so it was difficult to understand what were the right state points where to look for the glassy dynamic, because as I showed you here, it really depends on how close you are. And if you don't have your theoretical map, you will be lost looking for it. However, there were also theoretical works, and in particular, Thomas Voigtman studied the hard sphere mixtures. I will go back to it in a minute. And there was also a theoretical work of hard sphere and porous matrix by Krakowiak that kind of joined with the simulation of Kurdizim and co-workers. And I will go to this example in a minute. So the first one I want to mention, because we will use it later, is binary hard spheres. These are MCT calculations of Thomas Voigtman, in which he was able to show that there is an A3 singularity, and now the control parameter that before was the well width or the width of the potential now is the size of the small hard sphere. So we have larger sphere and smaller spheres that are 35%, smaller than the large ones. And at this delta, there is a particular packing fraction of 1 and 2 that where you have the A3 singularity. And when you start to deal with mixture, it's very interesting because now you can have many more glassy states that you had with one component system. Namely because in particular for asymmetric mixture, you can imagine that the small particle can be much faster than the large ones. And so there can be a clear separation of dynamics. And so there are states that are called partially frozen, fully frozen, when both species are glassy, or when basically the large species is glassy, but the small one is mobile. And this is what I will talk in the rest of the talk. And let's start with the canonical case of glass transition in a porous matrix. Here they consider that they have hard spheres, so another modification of their sphere model, but in some cases you have fixed particles, and in some cases you have mobile ones. So Krakowiak showed that basically in this MCT results, you also have an higher order singularity by the competition of these two glassy lines. One that is continuous, that is called type A, where basically you go from liquid to glass in a continuous fashion, which means that the plateau of the density correlator does not jump to a high value immediately, but starts from 0. And then you have, and this is a localization transition of the small particle in the glassy matrix of the immobile one. And then here you have instead the standard glass transition. So also the competition of these two mechanisms seems to be able to give an higher order singularity, and this Kurdizim, Kosovich, and Kahl simulation showed that there is a subdiffusive behavior. Now, this was the introduction to the second part of the talk, in which I want to talk about the Lorentz gas model, because it's something that we did a bit more recently that continues this, direction of anomalous dynamics. So the Lorentz gas model, I'm sure that all of you are familiar with, is a classical model for transport processes, in which you have non-interacting tracers that are point-like, that are moving in a fixed random matrix of obstacles that are, for example, overlapping R-spheres, sometimes called Swiss cheese models. And Thomas Franosch and co-workers have worked a lot on the Lorentz gas model, and they have a beautiful review article here. So the Lorentz gas model is well known because you can analytically calculate the occurrence of a transition that is related this time to more to percolation, let's say that to gaseous behavior. Because in the Lorentz gas model, the only control parameter is the obstacle density. So what is the packing fraction of the immobile matrix? And then you put these point-like tracers which explore the available space, and at some point the matrix basically the voids in between the matrix percolate, and so the intruders is called the tracer can go everywhere in the phase diagram and diffuse like this. Instead, if you have too much packing fraction, too large obstacle density, you will have that the void space is not continuous, does not percolate, and so you will have islands in which your intruders can move, and so they will become localized. And then there is a critical packing fraction of the obstacles at which there is this percolation of the void transition, at which the tracer dynamics becomes subdiffusive, and this is well known, and also the exponent can be calculated, and it's been calculated in this work. And the Franosch group, Fry, Hoffling, and so on, they did a lot of simulation on that. In particular, now the MCD shows subdiffusive behavior, but the density correlators studied in this paper, they show not a logarithmic behavior like we saw before, but rather a power law behavior of the density correlators close to this transition. Okay, so a different behavior than one predicted by MCT, but for standard glasses. So this is another transition. Some years ago, through the collaboration with Marco Laurati, Stefan Egelaf, and co-workers at Düsseldorf, we became interested in a modified Lorentz model that can be realized in experiments. That is, again, another modification of a binary Hart-free mixture, but with the following conditions. So we take small spheres that are very, very, very dilute. Okay, so their packing fraction is 1%. So that they are almost non-interacting with each other, but although they have exuded volume interactions within the matrix. And then we take the large spheres at a very large packing fraction, above 54, so that the large Hart sphere are glassy and kind of disordered matrix, resembling the matrix of the Lorentz model. So the crucial difference between the idealized case that we saw in the slide before is the fact that in the Lorentz model, you have a fixed matrix, and so the intruders, once there is a percolation of the void or there isn't percolation of the voids, they can just move in the available space. However, when you have that the matrix is glassy, what you have is that the particles can actually perhaps at some point diffuse away, even if in some configuration the voids do not percolate. So there is this new ingredient, let's say, as well as the exuded volume interactions of the intruder with the matrix and with themselves, but they're very, very, very dilute. So we were interested in this because our collaborators in Düsseldorf studied experimentally this system, taking two Hart spheres, one much smaller than the other, and they worked at these two size ratio, 0.2 roughly and 0.3 roughly. And the breakthrough of this work was the following, that even though these small particles are very small and they cannot be resolved by confocal microscopy, their 3D trajectory cannot be resolved, and so you cannot calculate just standard microscopy, confocal microscopy, their mean-square display, for example, the dynamics. They took advantage of differential dynamic microscopy. That is a technique that was invented some years ago now by Roberto Cerbino and Veronique Trappe, and refined in this paper in collaboration with Peter Lu for confocal microscopy, which you basically from basic microscopy images, or also from confocal microscopy images, you take this difference between a sequence of images that are taken at different times. You take their Fourier transform, and you can prove that basically this Fourier transform is related one-to-one to the intermediate scattering function. And so you don't need to do dynamic class scattering. You can do it also, you can do this technique at also a very large packing fraction, and you have a very high resolution both in time and in length. And you can measure by microscopy basically the full wave vector and time dependence of the density correlation function. And so you can resolve also something that you cannot see at the microscope. And in particular for this binary mixture, Marco Laurati and co-workers, they had different fluorescent color for the two species so that they could do the image analysis and calculate the intermediate scattering function separately for large and small. I think it was the first time that the small particles were resolved in this way, before the onset of super resolution, of course, more recently. And so the interesting results of the differential dynamic microscopy of Marco and co-workers were the following. At low size ratio, 0.2, in this modified Lorentz gas limit, what happens is that the density correlator goes to 0 when the large particle is around 54, let's say. You increase the packing fraction of the large particles. You confine more and more the small particles, which become, so this is the density correlator only of the small particles, because the large ones are frozen, basically. You see that there is the onset of a two-step decay, and that it starts from 0. This is what I told you before is called the localization transition, or type A, that this plateau doesn't go directly to a high value, but starts from a very small one in a continuous way. Okay, so at low delta, this was the scenario, but then that's the surprise, that for delta 0.3, they were very lucky with the experiments that at this Q vector, they found the onset of a logarithmic decay for a huge amount of time, like 4 decades. And so we started to wonder what was it due. I mean, was this a higher order singularity in this model? So of course, I told you we like to do simulations. So we did simulations. First of all, to see if this could happen. So we did molecular dynamics simulation of binary Hall spheres, so large and small. However, we also had to use a polydisperse, so a binary polydisperse mixture, because otherwise the large Hall spheres were almost one component, because the small ones were very few, and they would crystallize. So we did binary polydisperse Hall spheres. And we measured the collective intermediate scattering function of the small spheres. You see that I report similar size ratio than the experiment, 0.2 and 0.35, and that the phenomenology is really the same. So we have this localization transition here, and we have this logarithmic behavior here. Then, of course, in simulation, you can also do delta 0.1, 0.3, 0.4, 0.5, everything. In the experiments, it's usually more difficult. And so we further explore the range of possible parameters, and if you increase too much the delta, you find that a standard glassy two-step glassy dynamics is recovered, that you see is not continuous anymore. And so this indicates that there exists a critical size ratio for logarithmic dynamics. Okay. And the same in the mean-square displacement. So we saw that it happens at both places. So for small delta, the small particles are just diffusive because they are not localized. For large delta, you start to see, so for intermediate delta, you start to see this huge range of subdiffusion that accompanies the logarithmic behavior of the density correlator. And then you increase delta more and you have caging. So let's now try to understand if this is related to an MCT singularity. So if you focus on hard-sphere binary mixture, I showed you before the phase diagram that Thomas Voigtman had calculated, and the A3 singularity is here, but our simulation and experiment are here at very low volume fraction of the small particle. So if we increase the packing fraction of the glassy matrix, basically we are far away from the higher order singularity. So it seems that we cannot recover this behavior from MCT here. Let's look also of the fluid in the porous matrix. These were the calculation of Krakowiak for equal size hard sphere, which is not our case. But luckily, in the paper by Kurdiz in Metal, they extended this calculation also for different size ratios, and their lambda is 1 over delta. So if you change lambda, you decrease delta and you go towards our critical size ratio, your A3 actually moves here, and we are here, so we are here, so we are even more far. So really, this indicates that actually in this case, MCT cannot help us. We find a logarithmic dependence that is a different object. But just to be sure, Thomas Voigtman calculated the density correlators in this path, and actually confirmed that the theory would not predict the onset of logarithmic relaxation. So what is happening? I show you this nice picture of the 2D experimental trajectory, and this is more or less what I told you before, is that basically at low delta, the particle can diffuse in the all available space. At larger delta, instead, there are these voids that are isolated, and so they become more and more disconnected, and the simulation confirms the same. So why do we get now this logarithmic dynamics? So we attribute this differently from the Lorentz model to the fact that our matrix is not immobile. So we performed the accompanying simulation also with an immobile matrix, and we find the confirmation of the Lorentz gas behavior. So we did simulation of hard and small spheres at different delta, with the hard one at very large packing fraction that change in this way. That is fixed at this 0.62, we change delta, and you see that as delta increases, the particles becomes more and more localized. And actually you see the occurrence of the subdiffusive behavior that is predicted by the Lorentz gas at the critical size ratio roughly 275. If we compare with the case that we simulated before, that is the one with the experiment, that we have a mobile matrix, what you find is the following: that you have a much smaller critical size ratio for the mobile particle, that is 275 instead of 35 to find the subdiffusive behavior, and that basically in the mobile matrix, so in the modified Lorentz model, we have always that the small particles can eventually move away, because the matrix, as I say, is not fixed, and though it's glassy and it moves a little, its fluctuation can still free up the volume for the small ones to diffuse away. And so how about the density correlator? I showed you before that these were logarithmic, and then we calculated also the ones for the immobile case at 35, and we found basically the confirmation that we knew already, that in the mobile matrix, the dependence of the correlator is power law, while in the mobile matrix is logarithmic, as I showed you before. And so the fact that you have this matrix mobility in the modified Lorentz model is able to bring this new physics, where the logarithmic dependence of the density correlator comes from a subtle interplay, this time not from two arrest mechanisms, but from this localization and the fact that this matrix can move. And we don't have currently a theory to explain this simulation and experimental findings. So I told you a little bit of anomalous dynamics of stuff that is a bit old. I went for this talk, I went to the literature and tried to look what is going on. And I found a few nice works, and I want to highlight two of them. This one is from the group of Kunimasa Miyazaki, and they study a generalized Hertzian model binary mixture, of course, otherwise it crystallizes, in which they have an ultra-soft potential, so an inertial model with a small exponent, and they find the occurrence of logarithmic dependence and also subdiffusive behavior of the mismatch displacement. And in these particular models, this kind of ultra-soft potentials, you can form clusters, and the particles can overlap with each other. And in particular, in the simulations work of Miyazaki, they saw that there was a region in the phase diagram when you go from a prevalence of monomers to a prevalence of dimers. And so in between these two phases, monomer and dimers, they find this logarithmic dependence of the density correlators. And so they put in their paper, is it an A3 or an A4? That's very interesting, and it would be good to check. And finally, the last thing I want to flash is this work by Jan Sfreck, Yuri Chubak, Christos Likos, and Kurt Kremer. I think some of you are in the audience. They study ring polymers with activity. So a very, very actual, one of the modern, the modern system that we are working now. 20 years ago, we were working with square well, square shoulder. Now we do much more complicated stuff. And in particular, it deals with soft particles that are monomer resolved, and there is activity. So really, really interesting system. They have found for these ring polymers as a function of activity, the onset of a glass that occurs with a type A transition, this sort of localization transition. They found the occurrence of mismatch displacement, and they say in their paper that perhaps there is a nearby area of the singularity. So I think that the fact that such a recent work on a very hot model gives hints of anomalous dynamics, I think it would be really nice if we can apply the ideas of 20 years ago to these new models in the new simulations that we will do. So with this, I conclude. I hope I try to give you my best possible illustration of what I mean with anomalous dynamics in soft matter. You have it when you have competition between different arrest mechanisms. You find this logarithmic subdiffusive decay, sometimes reentrant behavior, and in general, it is well described by MCT higher order singularities. And I showed you also this case that was more recent, in which we worked with the Lorentz gas limit, in which we get new insights due to this mobility of the matrix that gives also anomalous dynamics, but kind of different from what known before, which kind of calls for the need of a new theory which combines percolation and glassy aspects. And then I try to convince you that there is also recent activity that has to do with anomalous dynamics that will be very nice to explore in the future by the next generations. And with this, I want to acknowledge all my collaborators. There are many more than his. I try to put the most significant that I talked in this talk. Also, I'm very happy that there is Matthias Perl and also Thomas Voigtman here that are students, PhD students with Professor Gozzi. At the same time I was a PhD student. And so let me also finish this, my personal tribute to Professor Gozzi, by thanking him and by putting this private picture that was taken at the symposium on the occasion of his 80th birthday some years ago with Francesco, his dear friend Francesco. And I always like to look at this picture that I conserve because I like very much the smile on the face of Professor Gozzi. And so please allow me this moment of memory, and thank you very much for the attention.
Okay. Thank you very much, Manuela, for this very thorough, complete description of what has been the story during these last decades and the state or challenges on our understanding of anomalous dynamics in soft matter, in colloidal systems in particular. As I had mentioned at the beginning of the talk, by the session actually, you can now indicate if you want to ask a question simply by marking your interest in the Q&A functionality of Zoom, and then we will allow you to mute yourself so that you can ask the question directly to Emanuela in order to facilitate the communication and make this slightly more informal, despite having to organize these meetings remotely. I don't see any question yet. So I had a curiosity related to this very last part, because you have talked about this logarithmic dynamics that how this could be understood in the context of this Lorentz. But at least in the example you show with respect to the phase diagram, this really happened at very low values, so far, for example, from this lambda point. Yes. So I wonder, do you envisage or think that there are implications in these dynamics, or that can also change when you approach to such points? Or you think this is something more fundamental and generic?
This is a difficult question. So I think that if you approach the higher order singularity, yes, you will find what is expected from the theory. In this particular limit, I don't know. Actually, we were surprised and we were triggered to do this work because the experiments found this logarithm, and we were not expecting that in the theory, as in fact we didn't find. And so I think that perhaps it could be due to, I mean, it's something that in this kind of theory is not taken into account. Basically, the fact that this matrix rearranges, and even in the static concept of MCT, perhaps since it starts from the structure, you would find a need to be able to accumulate, to take into account this further relaxation mechanism in your theory to understand that. But I think that it was quite interesting, and this say that even with a very simple model like the Lorentz gas or a modification of it that is doable in experiments, you can find very interesting dynamics. That's what I can say. Okay,
thank you. Okay, since I don't see any question, I'll take the advantage. This is more more general. When you were talking about basic, when you were talking about these different glasses, in particular between the attractive and the repulsive glass, and you show phase diagrams, sometimes there is this line, no? That you kind of color the two types of glasses in different colors. How should one understand this transition? Because you talk to them as if they were two glasses. Is there really like something like a phase transition in terms of the dynamics, or all these lines are at the end crossovers into two types of different dynamical response?
So perhaps I share it again. So you were asking something about this line, right?
Yeah.
So you're saying if I cross this line, what does it happen, basically, right?
Yeah.
So we investigated that, and so the theory would predict that there is a discontinuous jump, but of course in the simulations this doesn't happen. What you find that there is a crossover from the one to the other. I mean, the problem to investigate this is that you are out of equilibrium, so you have to monitor the age independence. So it's a little bit tricky, but our evidence is that basically with some time it will tend to go to the glass. And then we studied this also with Wilson-Poon much later, that there is actually another problem, that this attractive glass line, like in glass form, like Lennard-Jones, is actually the hopping mechanism which destroy the glassy phases is much more strong than in the topological cage. And so what happens is that in the end, the attractive glass, basically, if you are in the glass, if you wait a lot, then these kind of lines, I mean, not this one of the experiment, but in a simulation, you would tend to go towards the topological cage, because in the end you are always able to relax the bonds, but you will never be able to break the topological cage if you are at too high vacuum fraction. So it's a complicated thing that I didn't discuss with you due to lack of time. But yes, but in any case, you find the logarithmic dynamics in this crossover as well.
Okay, Thank you. So there is also a question by Walter Kopp. So you can unmute yourself and ask the question, Walter.
Hi, do you hear me?
Yes.
Yes.
Ciao.
Ciao.
So my question is, so you argued that the experiment by Edelhalf, you weren't able to see the Lorentz scenario because basically the big particles were wiggling around and therefore opening the gaps. But isn't this just a question of fine-tuning the density? I mean, if you increase the density of the big particles, they will wiggle around less and less. And I would expect that at the end, you should find something like a Lorentz gas behavior.
I agree with you. I think that if you go to very, very large packing fraction of the large spheres, they become effectively immobile. But then, I mean, when you go there, you first meet these other mechanisms. So there is this range in between where you are in the middle, let's say. But I agree with you. At very, very large packing fraction, you will eventually arrest. Although, let me tell you that if you remember my slide, now it's too complicated like that. But we were at packing fraction 62% of the large star, of the large spheres. How do I ask? How do I do this? Sorry. Which one is it that I want to show? This one. So if I show this one, you see that we were at 0.62 packing fraction of the large. So they are really, you would expect that they are really frozen. But nonetheless, the small particles, even if they are just, I mean, still 50%, they still can little bit diffuse. I mean, I'm not saying that they reach a diffusing behavior at long times, but still you don't find the gauging that
but this is an effect of 3 dimensions, because in 3 dimensions, even if you make a random close packing of the big spheres, basically you have still big holes. And that's what the small sphere exploit. But if you are in 2 dimensions, probably this mechanism is strongly suppressed.
That's a very good suggestion, and I invite the next generations to study the 2 dimensions model of this. Thanks, Walter.
Thank you.
Thank you. I think there is a poster that also touches on the question of dimensionality, so definitely something to take into account. So there is now another question by Achille Giacometti.
Yes. Ciao. Hi, Manuela.
Ciao.
You know, maybe I missed the point, because when the matrix is moving, when you have the matrix moving, there is a time scale involved, right? And you know, of course, you know, if the time scale is very large, this is like an immobile matrix. So do you have to average over these time scales? You know, when you do this end-to-end distance, do you have to do this average on the matrix as well? This is like a anneal versus quenched average.
Yeah, you are right. I mean, we didn't do it. We didn't do it. We simply calculated. I mean, I'm not showing results for the large stars, for the large spheres, because they were glassy, but they were honestly glassy. I mean, not particularly. I mean, I had a slide that I decided not to show because I had lack of time. You see that basically this is, I show both large and small spheres, and so these are the small ones at low size ratio that are basically diffusing and relaxing very fast, and these are the large ones. As you increase the packing fraction, they become glassy. So we have not average, but overall, I mean, at least up to this packing fraction, they are kind of in equilibrium because they fully relax.
Okay, thank you.
Thank you very much. We have also now a question by Chantal Valeriani.
Yeah, can you hear me?
Yes, ciao,
Okay,
ciao.
thanks. Ciao, Manuela. Very nice talk. I really liked it. Can I ask you actually 2 very short questions? One is about the very last part of your talk where you mentioned that Kurt Kremer and co-workers started looking at these anomalous dynamics in active ring polymers. Do you know whether, are you aware whether there are any other studies on looking at anomalous dynamics in active systems, apart from the active rings?
That's a very good question. I tried to look in the last few days, and apparently I didn't find, but maybe I missed them. So perhaps there are, but for the moment I can tell you a temporary answer that I think is no, but I think that there could be cases of anomalous dynamics in active matter, yes.
Okay, thank you very much. And then another very brief one. When you mentioned the Lorentz gas model, if I could consider something like a gel-like structure and small particles moving around, would this system behave as one you described with the immobile obstacles? So if I would consider something like a mesh.
Well, but in the Lorentz gas, I mean, conceptually not different, because basically you have overlapping spheres and they form, in the classical model, they form this kind of structure that is kind of a gel, let's say. No?
Yeah,
So
okay.
I would say that it would be the same.
Okay, fantastic. Thank you very much. Thank you.
Thank you.
Thank you very much. Then now there's a question by Christos Likos.
Good evening, Emanuela. Good to see you, and thank you for your wonderful talk as usual. I have a more general question. Maybe you can give us a comment, Emanuela, because you dedicated your talk to not only to Wolfgang Goetze personally, but also to mode coupling theory. But I think it is also fair to ask you as a statistical physicist from the Sapienza, what do you have any comment or view about the relation between mode coupling theory and the replica theory, the Parisi theory of glasses? I mean, is there something you can say from experience, or not in a non-political way? It's a very scientific question, actually, right? I'm curious.
You are not a friend, Christos.
Oh no, I withdraw the question immediately.
It's a difficult question. I mean, I cannot answer. I mean, yeah. I know that there have been a lot of discussion on this point, and I also know that in different dimensions other than 3, they have started to find kind of consensus, maybe not. So they try to get in close to each other. So I don't know, but let's say that from my experience, I see them as 2 different things, but they're useful, of course, both. And for the mode coupling, as a simulator, I can say that since it starts from microscopic principle, I mean, from the interaction potential between the particles, then it gives me a tool to see basically the dynamics of my system still in equilibrium approaching the glass. And so let's say that I have always used mode coupling as a map towards the glass transition, and as also we mentioned in the previous minutes, when you enter the glassy phase, then you need the more different tools, I think, because also the theory that started from an equilibrium structure that is not there anymore becomes shaky. So I know I didn't answer to your question, but it's too difficult, and I'm from La Sapienza, so I cannot answer.
You have not worked with the Parisi theory, have you? Or you're a mode coupling person exclusively? Okay.
No, I haven't. I didn't have the privilege, unfortunately.
Okay, thank you very much.
Thank you. I think that there is a follow-up comment by Francesco Shortino. So Francesco, yeah.
Hello, everybody. It's nice to see all of you. Actually, I don't see you. I see only Emanuela and Ignacio, but I like to imagine all of you. No, I just want to add to the answer that already Emanuela provided, essentially for the benefit of the younger, is that there are, in some sense, strong similarities between mode coupling theory and p-spin models. I mean, disordered spin models. I mean, the way the relaxation takes place in p-spin model, which are not the disordered, are also a type of disordered spin model, not really the one for which the replica were at the beginning developed, but Shane talked about it, but also for that you can do. In that type of models, the mode coupling equation becomes identical, really identical to the equations of the relaxation of the P-spin. And even the P-spin offer also the possibility to develop a thermodynamic approach that says that the free energy has just one single minimum above the critical temperature, and then it becomes a complex structure of many multiple minima below the Moore coupling temperature. There are connections also in the picture of the Moore coupling transition as a percolation transition in phase space. So there are many similarities between the P-spin models and the Moore coupling theories.
I agree.
Thank you very much, Francesco. I do not see any additional questions, so I think it's a good moment to thank Manuela again for a very nice talk and for this engaging discussion. And we will now move to the next speaker, the first of the shorter presentations. This will be done by Assam Sulk from Ben Gurion University. He will be talking about cooperative effects driving the multiperiodic response of cyclically sheared amorphous solids. So please, Asaf. Now.
Hello, thank you. I'll just share the screen. Okay, you see my screen?
Yeah, we can see it. Just please go on.
Thank you. So hello all, thank you for the opportunity to present my work here. My name is Asaf Schultz. I'm a PhD student at Ben Gurion University in Israel. Idor Regev is my advisor. And this is a collaboration with Metin Mungan from Bonn University in Germany. I will discuss today our recent results using a simple simulation model to understand the nature of the multiperiodic response of amorphous solids to cyclic shear driving. Okay, so how does the system respond to shear strain? So we apply a strain. If it is small enough, the response is elastic. So we are around a minimum of the energy landscape, and we shift it just a little bit. So if we reverse it, the system returns to the original configuration. But if the strain is large enough, the system will go plastic response and transform to a new minima of the energy landscape. When we release the strain, we remain in this region and will not be in the same configuration. What we see in experiments and simulations that under cyclic driving, amorphous solids reach some kind of a periodic state after some cycles. So you can see that here in this example, in blue, you see the particles that change position after the last cycle. So for low strain amplitudes, you can see that after some cycles, almost all the particles return to their original position. When you increase the strain amplitude, you see that you need more cycles. So here you still have particles that change location, but if you increase the number of cycles, you can get to this periodic state. In experiment simulation, you look at the particle trajectory, you can see that they form loops in space. This is experimental data. This is a simulation. You can see the trajectory that the particle go. And if you look carefully, you can see that this is a multiperiodic cycle. So you start at this orange dot, you do one cycle of driving, you reach the purple dot, and another driving cycle, you return to the orange dot again. So the response is as follows. You start at low strain amplitude, the response in a periodicity that equals the periodic drive, the periodicity of the driving. And when you increase the strain, you reach higher and higher periodicities. And when you surpass some critical value, you don't get any periodic state at all. And the material just flow. So we focus on the multiperiodic phase. So if you take some material, this is just an image from a particle simulation, you apply shear. Up to some point, it responds elastically. And at some point, you have an abrupt particle arrangement, which is called the T1 event. So you can see that these four particles change the position. So the neighboring particles move away, and these far away particles move closer. So you can look at this sort of an ellipse, which change the orientation. So you can also observe it in experimental data. So what happens that when it occurs, you can see that in some value, I call it gamma plus here, you get a displacement field that looks like a quadrupole, where the T1 event is in the middle. And if you take the same sample and shear it in the other way, for example, to some gamma minus, you get another quadrupole at a different location. So this is a different plastic event. So from the same configuration with different strength thresholds, you can get two soft spots, we call soft spots, with different displacement fields. So this one is smaller, but both look like a quadrupole. So these soft spots appears to be two-state entities. So we can approximate them as a double well potential. They have two states, the two ellipses that you saw previously. So this potential have two internal parameters and one external parameter. This is the strain that we apply. So if we change the strain for this example, we increase the strain, you can see that this minimum transforms to a saddle. And when it happens, the system switches to a different state. And it can happen in the other direction also if we decrease the strain to the point that it pushes it to the previous minimum. We can also see that if we manipulate the internal parameters, we can destroy the two minima and make it one stable minimum point. At this point, the soft spot is no longer active. This is a different state. And it can happen due to interactions that will mess up the internal parameters of the soft spot. Now we want to make it even simpler. So we take the soft spot and make it histons. So histons are the basic static element. Each histon has gamma plus and gamma minus value. So it has two states, 0 and 1. It starts, for example, in the 0 state. You increase the strain. When you reach gamma plus, it switches states, gets to S equal 1. And then you decrease the strain, it gets to gamma minus and switch to 0. So this is the basic hysteresis loop. And if you have a system of non-interacting histons, you apply cyclic driving up to some gamma max, gamma minus gamma max. You see that if gamma max is below gamma plus, it will remain always in S equals 0, it will not switch ever. And similarly, if it cannot reach gamma minus, it cannot switch. It will remain in S equals 1. But if gamma plus is bigger than gamma max is bigger than gamma plus, you can switch from 0 to 1, and again from 1 to 0 if it surpasses gamma minus. So this will create periodic oscillations. And this periodicity must be equal to the periodicity of the driving. It cannot be multi-periodic. We call it T equal 1. So in order to get something multi-periodic, we introduce interactions. So how we do it, you take this gamma plus and gamma minus and add some interaction parameter. What you can see here is just a displacement field of two soft spots. So you can see that 1 and 2 interact via these quadrupolar fields, displacement fields. So we have here some random matrix, interaction matrix. This is Aij. And we have a strength factor that we give each histon to represent its size. And it also depends on the state of the histon. So if it switches to 1, it adds it. If it switches back to 0, it subtract it. And we have a new gamma plus and gamma minus. What happens is that we can have a different gamma plus to the same histon. In this case, gamma plus is still below gamma max, so we can still have the periodicity. But it can also be larger than gamma max. And in this case, this histon is not active. And if it moves periodically between the two states, we reach some thing that we call threshold oscillations. So the histon do threshold oscillations, which can be with periodicity larger than 1. So briefly about the models that we use. So our model is random. Everything is random. The state of the histon is random, gamma plus and minus, random. The strength also random, and the interaction matrix. Because we have interactions, we need to discuss avalanches, meaning that after we update gamma plus and minuses, there are some other histons that become unstable, and we switch them by order, meaning that the most unstable one will be switched first, and then we repeat the process until everything is stable. So it can cause an avalanche, mainly 1 affect 2 with affect 3, and all switch at the same time. We also need to discuss what we call frozen states, which happen when gamma max become lower than gamma minus. We call this histon frozen. It cannot switch until gamma plus become larger than gamma minus again. So let's look at a simple example. So here we have a 3-hysteron system, which is the most simple system that we can have multiperiodicity in. Here you can see in gray, these are the transitions when the strain is increasing, and in orange when it's decreasing. So we have 2 transitions when the strain increases and 1 when it decreases, and the second cycle is above. Because of the nature of our model, we can keep track of the individual changes to gamma plus and minus. So you can see how it changes due to the interactions. This is very complicated to look at, but this schematic gives you the point. You can see that the thresholds, the strange thresholds of the hysterons oscillate around minus gamma max or gamma max. So this is 1, 2, and 3, which 2 threshold oscillations. And the interesting part, what closes the loop, is that the oscillations in hysteron number 1, it is what causes the oscillation in hysteron number 2, which causes this oscillation in hysteron number 3, which causes the oscillation in hysteron number 1. So now we have a closed loop. These simple systems recently began to attract attention. So here are some references of other groups that deal with similar simple systems and similar models. So you can see all recent publications. So this field is getting attention. But we are interested in more larger systems. So what we see here is a realization of 100 hysterons, which gave us a T=2 cycle. So what we see here, I marked the hysterons that we call period 2 hysterons. What I mean by period 2, take for example 87. It is not marked. You can see 87 here, 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 and here. So 87 appears in every segment of the cycle. But hysteron 9 appears only in 2 places, meaning only in the first cycle, and 16 as well, only the second cycle. 93, you can see it only in 2 places. So we call them period 2, and they are the hysterons that drive the multiperiodicity. Note that hysteron number 1 is not very interesting because it switches here and here again, so it does not affect the dynamics. So the question that we ask, can we reduce this complex system to the simple 3-hysteron system? Naively, we can say that yes, even we can even use the same graph that I showed you before, just change the numbers. So now it is 9, 93, 9, 16, 93, and 16. So it closes the loop. But is it really the case? So we can answer it because we can track the changes with the gamma plus and gamma minus. So 16, just to go real quick, you can see that 9 and 93 have a significant effect on gamma plus of 16. So here it is enough to push it above gamma max. This is the level of gamma max. So it cannot switch in the first cycle. In the second cycle, we don't have 9. So it puts 16 low enough to be able to switch. So 16 switches in the second cycle due to the interaction with hysteron number 9. Hysteron 93 is a little bit different. This is what we call the frozen state. So you can see here in this segment, gamma minus is above gamma plus. So it cannot switch, it's frozen in this segment. But when you get to the second cycle, you see that 16, the effect that it has on gamma plus and gamma minus of 93, they push it a little bit up and a little bit down, the gamma minus, so it gives it a window, small window to switch. So 93 switches because of 16. But hysteron 9 is the interesting one. If you look at the first cycle, hysteron 9 switches after 87. So this is when gamma plus of 9 is below gamma max. In the second cycle, we want to see hysteron 9 after 87. We don't see it, but gamma plus is still below gamma max. So this is a bit strange. You'll see that 69 switches before, 21 and 41, and only then gamma plus of 9 is above gamma max. We call it the cascade of hysterons that push gamma plus of 9 above gamma max. And the effect we call cascade scrambling. If we look a little bit closer, you can see that the original sequence is 87, 9, 41, 93, 69, and 21. And what happens, because if you remember, 93 was frozen here, so it cannot switch. So here it is already in state S=1. It cannot switch again, so it is not here. And what happens is 69 and 21 are pushed before 9. And after that, 41 is also pushed before 9, and 9 cannot switch. So this effect of scrambling of the cascade is what causes histone 9 to do the threshold oscillations. So to summarize real quick, so we saw that the biggest benefit of our model is that we can track the changes of gamma plus and gamma minus all the time and after every switching. And we saw interesting things. The threshold oscillations, by the way, we can also see in molecular dynamic simulations. The frozen state and cascade scrambling are effects that are, at least now, harder to observe in molecular dynamics, and we are working on it to try to confirm that. And we have many more results in this paper about molecular dynamic simulation that I did not discuss in this presentation. We showed that the increasing number of histones is not just a background, but it has an important effect on the dynamics, mainly in the cascade scrambling, as we saw. And the physical implication is that when we have more histone, we expect to see more of these cascade scrambling effects, which we believe is the reason why you see multi-periodic cycles more in high strength values than in the lower ones. Because when you have more histones, we have more cascade scrambling, you can have more configuration accessible for the system to explore and find, which are multi-periodic. And with that, I will end. Thank you.
Okay, thank you very much, Asaf, for this presentation. I remind everybody that if you want to ask a question, it's enough that you indicate in Q&A that you want to do that, or that you have a question, and then we will unmute you so that you can ask the question yourselves. I had a question. I mean, you talk, Asaf, of these three types of correlated motion: these threshold oscillations, frozen, and cascade scrambling. It's not clear to me, how do you really distinguish them, or to which extent you think, I mean, the objective is to get a classification so you can differentiate them as qualitatively different type of correlated motion?
Well, we wanted to understand why we have multi-periodic cycles. So the frozen state is, for now, an artifact of the simulation method, but we see also evidence of it in molecular dynamic simulations, mainly that we don't see the threshold oscillations as is. If we see in molecular dynamics that the strange threshold, or when the soft spot switch in values that are far away from gamma max, we can suspect that maybe it is a frozen state, and this is why the histone or the soft spot does not switch. The cascade scrambling is more an interaction effect that the soft spot are using in order to cause threshold oscillation of other soft spots. So if we look at complex systems, this can give you a much better, easier way to get the correct configuration to enable this specific set of conditions to allow this multi-periodic cycle. Because if you take only 3 soft spots and you want them to interact in just the right way, this is very hard to find. But this allows you much more flexibility to get what you want, what you need in order to get the multi-periodicity.
Okay.
I hope that it answers the question.
Yeah. Yes, thank you. Thank you very much. So I don't see any additional question. I remind you that these presentations will also stay as posters in the Gather session afterwards for those of you who have registered. So that offers an additional possibility for you to indirectly, informally continue the discussion. I see a question by Vishnu Krishnan. I don't know if, I mean, if you can unmute yourself, you can pose the question directly, Vishnu.
Hi, am I audible?
Yes. Yeah.
Hi. Yeah, so my question is about whether the density of soft spots near gamma max controls the periodicity that's possible. And I'm assuming that increasing the system size also increases this density of how many soft spots or histrons there are near gamma max. And in that case, what would you expect in really large systems?
Yeah, this is a good question. In this model, we don't have a meaning to density because everything is random. So the proximity or what you can expect for a dense system is not here. So maybe you can relate it to hysterons that interact strongly, which by design is not the major part of hysterons. But we do see in particle simulations that we have regions of more dense soft spots in this region, and we still have some not in so dense areas, and they are all interacting together.
So I didn't mean spatially dense. I meant dense in strain. So at every strain, you have soft spots at certain strains, and you could have them accumulate close by in strain. Density in strain is what I meant, not in space.
Okay, so I didn't check it, how many soft spots I have in each strain, but you can see that for lower strain values, you get mostly paired one cycles. So when you increase the strain, you increase the number of hysterons, you can see that you have the multiperiodicity. The relation is somewhat linear. When you increase the strain value, the number of hysterons or active hysterons increase linearly.
I see.
But
okay.
I don't have the exact numbers.
Thanks.
Okay, thank you very much. Thank you, Asaf, for the presentation and the discussion. I think we can then move on to the second short presentation in this first part of the event today. It will be by Fergus Moore from University of Bristol. We'll be talking about crystallization and polymorph selection in active Brownian particles. So Fergus, now, the floor is yours.
Thank you. Thanks to the organizers for giving me an opportunity to talk about some work that I've been doing during my PhD. Before we get going, I'd like to thank my supervision from John Russo, Paddy Royale and Tani Liverpool, and the BCFN and my funding. So active matter has been brought up a couple of times already today. So this is when we have artificial bodies or organisms that consume energy for self-propulsion. So that could be a bacteria that's metabolizing in its body and then able to swim, or we could have active Janus particles, for example, which are driven by external fields. And the thing that makes these things interesting is they're out of equilibrium systems that we're able to study. And this out of equilibrium nature creates new phenomena that we can learn and understand. So active colloids in particular. Here we have some examples of experiments done in Bristol. So we have 2D self-propelling particles here. The color relates to the degree of six-fold symmetry. So you can see these nice hexatic crystals. This is actually experimental data. And on the right, we have 3D active self-propelling particles. These are Janus particles, and they not only are they self-propelling and crystallizing in 3 dimensions, but they also have a dipole, which creates another layer of interesting structure. So if we're going to simulate these kinds of colloids, there's a popular model that's often used, which is a nice, simple, it neglects things like alignment and hydrodynamics. So we have one particle, if we're looking at just one, that self-propels, and the direction of which this propelling happens rotates with thermal rotational diffusion. So we have the equations of motion here. So the velocity, the first term, we have this V0 is a constant velocity, that the direction of which E rotates with thermal diffusion proportional to its rotational diffusion coefficient. And this is a random Gaussian noise. And then we have interparticle forces, and then finally a Brownian noise term with translational diffusion and an independent random Gaussian noise term. And that creates some dynamics such as this, which is I've made a little 2D simulation. So you can see that they're feeling Brownian effects, but if you watch one for a little while, it'll go in a particular direction, and then this direction will diffuse and it'll change, and they interact with each other. I also want to introduce the Peclet number, which is a useful metric for describing these kind of systems, which is a ratio of the strength of the propulsion in one direction to the thermal noise. So we can change either the constant velocity, or we can to increase this this direction, or we can reduce the rotational diffusion current so it turns faster, as it is one way to control these kind of systems. people have shown that active particles in 3D crystallize already, and there have been a few studies in the different phase diagrams. I just want to note that we know that activity suppresses crystallization. So at higher Peclet numbers, you need to go to higher densities, rho in this particular case. So we have spherical monodispersed particles that I'm talking about. And when they crystallize, they form two kinds of structures or polytypes. So we have face-center cubic crystals or hexagonal close packing crystals. The representations are here. And if you look at them on certain planes, you can see the structure is the same. The difference comes from the layering of these structures. So hexagonal close packing is an ABA structure, and face-center cubic has ABC. So there's an extra kind of slided plane. And these thermodynamically, there's very little difference between them. And when they nucleate without self-propulsion, you get an equal amount of either. And if you add some external pressure, sometimes you get a slight favoring of FCC. So in this work, I'm going to talk about how active spheres crystallize, the mechanisms for which these crystals nucleate, and an interesting polymorph selection phenomenon that's distinct from that of passive systems. So like I said, I'll be using active Brownian particles. They will interact through the Weeks-Chandler-Anderson potential. And the control parameters that are important to this work, we're going to use the total density, which is just the number of particles over the volume of the simulation box. And we'll be changing the Peclet number by keeping the rotational diffusion coefficient constant and changing the propulsion velocity. For structure, we'll be using the topological cluster classification, or TCC, which is a cluster-based structure which looks at central particle and then around from that, it compares and fits into known clusters. So we have the FCC and HCP, of course. I'm also including the 5 and 10 particle clusters, which are very prominent in fluids. So it gives us like the anti-crystal structures, if you like, which is a good reference point. And then we can look at the fraction of particles in these clusters as a proportion of the whole system as a way to describe what's happening. So here's a state diagram, which is a bit of a map of the area that we're looking at today. So we're varying the total density in the x-axis, and then for each one of these densities, we change the Peclet number and look at the structure of these states. So we have a freezing line here. So everything to the right of this black dashed line is crystalline. And then within there, we define two different types of nucleation mechanisms within which these crystals grow. And I'll be getting into those two different mechanisms shortly. And so if we're looking at structure, and we're going to be applying this TCC, one thing we can do is at a particular density, we can run the system for a long time at different Peclet numbers and then look at the structure that arises after a long time as it asymptotically kind of arrives at a final state or something like that. So we have the fraction of these different structures. So we have the two crystals, FCC and HCP in green and black. And then I've also included these liquid structures that are very prominent. One thing to note, since the TCC is a cluster-based model, particles can belong to more than one cluster, so don't expect these numbers to sum to 1. So without self-propulsion, without activity, Peclet 0, you see that the difference between the two crystal polytypes is very little, with a slight preference to FCC, as has been reported before. But as you add activity, you see that the population of FCC increases to the detriment of HCP, up to an interesting point here where the gap then reduces again, and beyond which the activity is too high to nucleate crystals and you get a liquid, which is when you see the prominence of these fluid structures 5 and 10. So why is this FCC prominence happening? Well, it's to do with these layers that I was talking about before. So we can see that HCP looks like this and FCC is like this, and HCP has a slight mechanical instability that is kind of slid across due to the promoted persistent motion of active particles. So I have a little video here. So the green particles are FCC and the black particles are HCP and white are non-crystalline. And I want you to look in this region here where particles are going to be active and moving, and you'll see this annealing of the HCP layers into FCC. So you see it happening here. And over a long time, this will kind of continue, and HCP will be slowly kind of weeded out of this crystal as it coarsens. So you can see the same graph as before, but I've added also we looked at another higher density, and so you can see it persists at higher density as well, and the amount of FCC actually increases, and you can see HCP going down more drastically. These shaded regions are the standard deviation as we averaged. The final bit of interesting data that comes from this plot is I've sort of outlined with these two vertical dashed lines. And what's happening here is marking an area where the nucleation or crystal growth mechanism is different. So to the left of this line, we're going to be looking at spinodal nucleation. And in between here, when you have a slightly different polymorph selection, we have nucleation and growth. So I'm going to get into the differences between those two now. So spinodal nucleation is a spontaneous phase change, multiple nucleation events. You see the crystal grows from different areas of the simulation at once, and there's a lot of coarse grain boundaries when it happens this way. Whereas nucleation and growth is nucleation is a rare event. Eventually a nucleus will crystallize and then grow out from a single nucleus. So I trimmed this video. It takes a long time sometimes for that to happen. What happens because of the differences here and the different kind of grain boundaries is in the spinodal case, which is the lower activity regions, there's a lot more annealing of these HCP boundaries. But when you get to this nucleation and growth regime, then you have slightly less of this, and it trends a bit more towards the passive case of less preference for either polymorph. So to look a little bit more into the nucleation and growth, we can see kind of how these crystals nucleate as a function of activity. So one way of looking at that is the mean first passage time, which is the time it takes for a crystal nucleus to reach a certain number of particles. So I'm looking at three Peclet numbers in this case. So the black is 4.8, blue is 5, and green is 5.2. And so what's happened here is, on the x-axis, for 2,000 particles to join the crystal, it takes 30 for 4.8, and you can see it takes longer as you increase the activity. And people have done a lot of work with the mean first passage time, and there's a fit you can do, which lets you extract the crystal nucleation rate K and the critical nucleus size and C, and we learned that both parameters or both variables decrease with increasing activity, and that tells us that activity inhibits nucleation. And finally, we look at the spinodal nucleation regime. So what I'm showing here is how these spinodal crystals grow very quickly for different Peclet numbers. So we have the green and black lines for FCC and HCP as before, and we're looking at three Peclet numbers: 0, the passive case, and the dotted lines are Peclet 2, and the smaller dots are 4. And you can see as you increase the Peclet number, the rate at which these crystals grow increases because of the accelerated dynamics. You also see, for example, in Peclet 4, the HCP will decrease over time as we have these annealing of stacking faults. So we can further analyze this by, my slides have crashed, unfortunately. Oh, there we go. So we can fit these with Avrami equation, which describes how solids transform from one phase to another. So we fit these, and this equation, we have this Avrami constant K, which includes the crystal nucleation rate and the growth rate G dot. From these fits, we can define this characteristic time, which is useful because if we collapse the curves onto each other, this time scale that causes this collapse, we can find out that as this decreases, since it's proportional to this, that the growth rate increases, which tells us that the growth rate does indeed increase due to the accelerated dynamics in the melt. And so in summary, so in agreement with previous work, we found that crystallization is suppressed by activity. Unlike hard spheres, we found an interesting preference of FCC over HCP. When freezing occurs more slowly, In the nucleation growth, we see less of this preference. Nucleation rate decreases with increasing activity, and finally, the crystal growth rate increases due to the accelerated dynamics. And if you'd allow me just one more thing to say, is there was an interesting discussion before with Emanuela, where we're talking about particles inside anomalous dynamics. I also get my hands dirty in the lab sometimes, and I make colloidal gels, which are 3D systems, and then I add Janus particles into these that would be made active by electric fields, and this allows us to explore in complicated environments, and we're doing some simulations of this. So we have a slice, these yellow particles are a gel, and as they move, you find their persistent motion. Some particles collect and have get very stuck and have slow dynamics, whereas others are moving very fast. This is a histogram of the displacements, and you see there's a population which is moving very slowly as the Peclet number increases, and there's a population that moves very fast. But yeah, thank you for listening to me. That's the end of my talk.
Okay, thank you very much, Fergus. So again, I remind you, you can simply indicate your interest to ask a question in the Q&A. So there is already a question by Vishnu. So please, if you mute yourself, you can pose the question.
Hi. So you'd shown an interesting enhancement of the FCC local structure, right? So if you started from a purely crystalline state, which is either HCP or FCC, would it finally still give you those same results, or would that affect things?
That's an interesting point. We didn't start it from a perfect crystal, so I'm not sure. We did look at if the melting line was different to the freezing line, but and it was, but I don't actually know what would happen. I guess with the HCP you might, and FCC, because you're adding the particles initially have random orientations, which might cause some grain boundaries to occur, which could then lead to a breaking of the perfect crystal into smaller domains, which then may shift. But I've not seen it. It's an interesting point. Thanks for the question.
Okay.
Thank you. There is also a question by Richard here. So Richard, you can ask the question yourself.
Hi, Fergus. Nice talk. So, I mean, is nucleation different? I mean, could you say classical nucleation? I mean, classical nucleation say works quite well with hard sphere crystals at equilibrium. I mean, how about here? And if so, what's the surface tension or the analog of surface tension?
That is a good question. So I don't know. I believe there was a work when we were writing this up where someone had looked at classical nucleation theory for active particles. I'm afraid I don't know what surface tension would be, but I think someone did look into this. So if you're interested, I expect that paper will be available.
I mean, you see, obviously, surface tension tends to cause clustering, right? So you see clusters appearing. I mean, obviously, but normal for hard spheres, you see subcritical clusters appearing and disappearing due to surface tension.
Mm.
You see that? Because that would give you an indication that an analog of surface tension is occurring.
I'm not sure. There is some thought to, because as you go to higher Peclet numbers, obviously you get MIPS in active systems. Mm-hmm. And it would be interesting to see how the local structure changes in response to those new structures that are forming. We did look at the structures just in the fluid below the crystallization limit, and we found just a loss of structure across all different types as Peclet number was increased. As a term for clusters and surface tension, I believe it could be quite interesting to look at, but I'm not sure really.
Okay.
How to answer that.
Okay, thanks. That's really interesting. Thanks again, Fergus.
Cheers.
Just as a curiosity, since you refer now to MIPS, when you look into the liquids, how far is the MIPS transition in this region you are exploring?
So MIPS happens around 60 to 100 Peclet number, depending on the density. So we're looking quite a lot below that. There's a dependence of the MIPS phase boundary on a few aspects, such as the system size and the mechanism for which the particles are propelled. So we are well below the MIPS boundary, but when you're looking at that, you do need to consider a few other things that we didn't have to because we're at relatively low Peclet number.
Yeah. Okay, thank you. So I don't see any additional questions. So thank you very much, Fergus. We will be then now moving to the last speaker of this first part of today's session. This is Luca Tonti from University of Manchester. He'll be talking about diffusion of globular macromolecules in liquid crystals of colloidal cuboids. Luca?
Yeah. Good afternoon, everyone, and thank you very much for this opportunity. I'll share my screen. Okay. Can you see my slides?
Yeah, we can.
Okay. Okay. So, good afternoon, everyone. My name is Luca Tonti. I'm a PhD student at the Department of Chemical Engineering and Analytical Science at the University of Manchester. And together with my supervisor, Dr. Alessandro Patti, and with the collaboration of Dr. Fabian Garcia, we recently investigated the diffusion of globular macromolecules in liquid crystals of colloidal cuboids. At the beginning of this session, Dr. Emanuela Zaccarelli already gave a clear and nice description of the anomalous diffusion and its occurrence on soft matter. So I'll try to be as concise as possible. When a colloidal particle displays in a solvent at infinite diffusion, at infinite dilution, we expect its mean square displacement to be linear with time. But in the presence of crowded colloidal suspension, the diffusion of this spherical tracer can be anomalous at some time scales. And so this is what we call, we mean by anomalous diffusion, when the mean square displacement does not depend linearly with time, but it depends on a with a certain power law with time. The occurrence of anomalous diffusion can be, it was observed in biology, for example, for the diffusion of macromolecules in cellular environments, in material science, for the dynamics of additives in polymer matrices, and in microrheology, where we investigate the displacement of single particles, single tracers in suspension to investigate the rheological properties of the suspension. In many studies, so many studies were focused on the effect of volume fraction and gas cost affinity and relative characteristic length for the analysis of the diffusion, but we wanted to focus our attention in this work on the effect of long-range ordering. So how the orientation and structural organization of the mobile matrix affects the diffusion of spherical tracers. So for this reason, we performed dynamic Monte Carlo simulations of hardcore-like particles, so cuboidal particles with different shapes, prolate and oblate. We use the thickness T of the cuboids as unit length of our system. And we perform simulation of cuboids with length, relative length equal to 12 and relative width equal to 8 for oblate cuboids and 1 for prolate cuboids. And we perform the simulation of cuboids and hard spheres that are much smaller than the extent of the cuboid. So they have a diameter equal to 1/10 of the thickness of the cuboid. And we investigated the dynamics of the mobile cuboids and the hard spheres in isotropic and uniaction nematic phases. To investigate the diffusion of these particles with an isotropic shape interacting with hardcore interaction, we perform these dynamic Monte Carlo simulations. So we, in the frame of dynamic Monte Carlo methods, we first need to define the maximum displacement and rotations of the particle using the Einstein relation. So the maximum displacement of the particles and their maximum rotation is defined by a time scale, Monte Carlo time scale, which is unique of the particle shape. And it would depend also on their diffusion coefficient, so the translation and then rotational diffusion coefficient of the particles at infinite dilution. And we can recover the proper time scale of from the Monte Carlo simulation, linking the mean square displacement computed in Monte Carlo simulation that will depend on their acceptance rate from the mean square displacement commonly computed from Brownian dynamic simulation. So at the end, we can recover a unique time scale for our Monte Carlo simulation that will be dependent of the Monte Carlo time scale that we set at the beginning, the number of trials that we perform, and we define one Monte Carlo cycle as an n trial moves, so n random rotation and translation of particles, and the acceptance rate, which is the percentage of trial accepted over the total trial attempted. So we investigated the diffusion of first of all, the hardball-like particles in uniaxial nematic phases. These particles interact only with hardcore interaction, and at certain, from their phase behavior, we know already that at certain packing fraction, at certain densities, due to their shape, so solely thanks to their volume excluded volume interactions, they can reorient and reorganize and form nematic phases that can be prolate nematic phases for prolate particles, and as you can see in the snapshot in the left, and oblate nematic phases for oblate particles where the nematic director is orthogonal to the length and the width of the particle. And we computed the mean square displacement of the cuboids in the nematic phases, decomposing the mean square displacement in the direction parallel. It is shown here with red data, red points and lines, and perpendicular to the nematic director, shown here in blue lines and data. We computed the mean square displacement, and also performing the logarithmic derivative of the mean square displacement, we estimated the apparent exponent. So how the mean square displacement deviates from linearity with respect to time. And we observed the formation of temporary caging effect for the particles in specific direction for depending on the main orientation of the nematic phase at intermediate times. And also, as I said, the anisotropic diffusion of hardball-like particles that preferentially move in the direction parallel to the nematic director for prolate nematic phases, and in the direction perpendicular to the nematic director in oblate nematic phases. We also computed the known Gaussian parameter, which give us an idea, an estimation on how the probability this particle displacement deviates from an expected Gaussian-like distribution. And we observed that in this case, despite the formation of temporary caging effects, we didn't see strong deviation from Gaussian line distribution. So we could say that all over the time scales that we investigated, the particle displacement is Gaussian-like, despite the formation of temporary caging effects. And we also computed the dynamics. We investigated the dynamics of the hard spherical tracers that are diffusing in this mobile matrix of hardball-like particles, and their dynamics is guided by the orientation of the nematic phase, and they showed similar dynamics to the similar to the dynamics of hardball-like particles. So hard spheres move preferentially in the direction parallel to the nematic directory in prolate nematics, and they move preferentially perpendicular to the nematic directory in oblate nematic phases. And in this case, these spherical tracers are much smaller than the cuboids. So it seems that there is no presence of temporary caging effects, or they are much weaker than the ones that you observed for cuboids. And overall, since the particles are much smaller and the dynamics is defined by Brownian motion, they diffuse much faster than the cuboids. We also computed the non-Gaussian parameter, and we observed in this case for the spheres a strong, like a more prominent deviation from expected Gaussian-like distribution of particle displacement for the diffusion of hard spherical traces in the direction parallel to the nematic directory in oblate nematic phases. And we think that this occurs most likely due to the higher number of collisions that the hard spheres may have with oblate particles with respect to prolate particles to their higher extent in space, which is for oblate particles, for oblate cuboids rather than prolate cuboids. To have an idea on how strong are these deviations from the Gaussian distribution, we computed the Selpanov function of the hard spherical traces in these uni-action nematic phases. And as I said before, we observed higher deviation from Gaussianity all at intermediate times, and specifically for the diffusion of hard spheres in the direction parallel to the nematic directory in oblate nematic phases. As you can see here from the dots reported in red in this case, which are the data of the Selpanov function directly computed from the simulation, that deviates from the line which represents the expected Gaussian line distribution in this case. From the linear regression at long time scales of the mean square displacement, we extracted their diffusivities, and we observed that generally oblate particles, since they are bigger in their extension than prolate particles, diffuse lower at long time scales. And as I said before, the diffusion is anisotropic in this case due to their long range ordering of the nematic phase. So prolate particles in prolate nematic phases diffuse preferentially in the direction parallel to the nematic director, and the opposite thing occurs for oblate particles in oblate nematic phases. And these similar characteristics of anisotropic diffusion are observed also for hard spheres, and generally spheres, due to their smaller size with respect to the cuboids, diffuse much faster than the mobile matrix in which they are immersed. We also computed the total diffusion coefficient of both the cuboids and the spheres in the nematic and isotropic phases. And as already shown by Dr. Emanuela Zaccarelli, the density of the system affects the diffusivity of the particles. So particles, both cuboids and spheres, diffuse lower in denser system, as you can observe here from slower values of diffusivity at long time scales, passing from isotropic to uni-action nematic phases of cuboids. For the total dynamics of the particles, we also computed the non-Gaussian parameter to see if we can observe deviation from Gaussianity. And interestingly, we observed a strong, more predominant deviation from Gaussianity at intermediate and long time scales for prolate particles in isotropic phases. And we try to give an explanation of this occurrence of deviation from Gaussianity in less dense system, so in isotropic rather than uni-action nematic phases. And for this reason, we computed, we try to find the nematic-like clusters in isotropic phases that maybe can affect the diffusion of prolate and oblate cuboids. And for this reason, we computed the probability distribution of clusters per size. And we observed that passing from isotropic phases from low to high piping fraction, we observed the formation of more and more clusters in number and bigger clusters in size. And prolate particles, prolate cuboids tend to form more clusters at higher densities and bigger clusters, so clusters with more number of particles at higher densities. And we think that this is the reason why we observe this strong deviation from Gaussianity specifically for prolate particles rather than oblate particles. So in conclusion, in this work, we performed DMC simulation of hardball-like particles and hard spherical tracers to investigate the effect of long-range ordering in the diffusion of smaller tracers. We observed the general subdiffusive behavior and the formation of temporary caging effect at intermediate timescales. We observed anisotropic diffusion due to the long-range ordering of the phase. So prolate particles tend to diffuse faster in the direction parallel to the nematic director in prolate nematics, and the opposite things occur for oblate particles in oblate nematic phases. We also observed that oblate particles tend to diffuse lower than the prolate hardball-like particles, and the structural order and dynamics of the host phase determine the dynamics of the spherical tracers. Generally, the density of the system affects the diffusion, the total diffusion of the particles, and the denser the system, the slower the diffusivity. And as I said before, we observed this unexpected non-Gaussian distribution of particle displacement for prolate hardball-like particles in isotropic phases, and we think that this is linked to the formation of randomly oriented nematic-like clusters in isotropic phases. I want to thank personally my supervisor, Dr. Alessandro Patti and Dr. Fabian Garcia Daza for contributing in this work, the Leverium Trust for the fundings, and the computational shared facility from the University of Manchester for providing us all the servers to perform all the simulation. Thank you for your attention.
Okay, thank you very much, Luca, for the presentation. Now there are time for questions. So there is a first question to Francesco. Maybe you can ask the question directly.
This is just a curiosity. Probably you said it, but I might have missed. How have you defined the clusters, the nematic cluster?
Yeah, so let me see. No, so well, the clusters were defined using some criteria. So we computed the clusters. We computed the relative distance of the center of mass of the particles in this case, and we decomposed this relative distance in direction parallel and perpendicular to a local nematic director estimated by the orientation of the particles. We knew already that prolate particles tend to align their length, while oblate particles tend to align their thickness. So we, for every couple of particles, we computed a trial local nematic director, and we used that to estimate how the particles were distant to each other. And from that, we started constructing the clusters until no other particle could be added to the cluster. I hope it's clear.
Okay, thank you very much. I don't see, you had a curiosity, you have talked about this non-Gaussianity and the sensitivity of the diffusion in these dense oriented phases. Since we have been listening to Emanuela earlier, have you been looking at in more detail about the structure of these dynamics, relaxation and dynamics, if there is something like these very slow decays that she was describing in the context of this relationship of glasses with the Lorentz gas?
Yeah, so I think that in our case, the system are not dense enough to see that glassy dynamics, but it would be interesting. We didn't perform any simulation of system at higher density. It is really interesting, and it's something also that we were thinking about doing. Also because the additional feature here is that the change in density does affect not only possible percolation of the systems and how these theoretical traces diffuse, but also the organization of the mobile matrix in this case, because these are ball-like particles, depending on their shape and the density, can form also symmetric faces, columnar faces. So all the long-range ordering of the phase will change, and the dynamics of the spherical tracer will change a lot. Yeah.
Yeah, thank you. I do not see additional questions, so thank you very much, Luca, for the presentation. So we arrive here to the end of this first part. So thank you for joining in this 13th installment. And I remind you that for those who are registered now, you can join us in the Gather Town, where then there is a space for informal discussions. And then there are 6 posters, and you can meet the presenters, and then you will have the chance to discuss. You should have received the link to connect to Gather in the email about this session. As I mentioned, previous sessions are available on our website, and stay tuned for future activities. And that you can do that by registering to our webinars mailing list, which is at the bottom of the MixGen webpage. And you can also follow us in Twitter at SICAM events. So thank you very much.